I'd like to tell you about some work I've been doing recently that transforms signals to images that are suitable for deep learning, and that's done using Attractor Reconstruction. This is joint work with my colleague Manashi Nandi at King's College London, my PhD student Jane Lyle. So basically we want to classify signals using machine learning, and so the way we do that is convert it to a signal, convert the signal to an image and apply deep learning. Signals go an awful long way along the time axis, and so it's very hard to see the detail. So if we transform them to a bounded phase space using Attractor Reconstruction methods, then they're much easier to visualize and capture as an image. So blood pressure and ECG data can be sampled at high frequency, and over many hours or days. For example, 1,000 hertz, 1,000 data points a second. If you zoom in, you can see some detail, but this is just 15 minutes of data, and you can see no detail there at all. So, and the problem is basically this data is stretched out along this time axis. If we plot the data in the phase space, then it gives us a bounded view of the data. So we're all familiar with this with systems of differential equations. So we often view trajectories in phase space rather than the time trace. So if we take the Lorenz equations that we're all familiar with, then the time trace looks like this, and we don't usually look at the variables in this way. What we do is plot the variables in phase space, x against y against z, curve parameterized by time, and we get some structure even from a chaotic differential equation. So the trajectory goes round and around one side, then it flips over to the other side, going round and round, and so on. So some structure can be seen there in that attractor. So we'd like to plot the data, our data in phase space. The only problem is we've only got one variable, but Takens came up with a solution for this back in 1981 and gave us the method for reconstructing attractors using delay coordinates. So instead of taking one point on n signals, we take n points on one signal using these delay coordinates. So we take a fixed delay tau, and we can choose n as whatever value we like as the embedding dimension. So if we take just the x variable from the Lorenz equations and do a three-dimensional embedding, we get this attractor down here. And again, we've got similar structure, looping round one lobe, switching to the other one, looping round, and so on. So qualitatively, we get a similar sort of structure. Obviously, it's different in the detail, but it's qualitatively similar. So there are two choices that we have to make with this method. We have to choose the embedding dimension, which is n, and the time delay, which is tau. So Takens proved that if we have an n-dimensional manifold, then that requires 2m plus 1 delay coordinates for the reconstructed attractor to be an embedding. The only trouble is most of the time we don't know what m is, so that's not much use. And theoretically, there are no restrictions on the time delay tau. So interesting theoretical results, but they're not of much practical assistance. There are methods in the literature for choosing the optimal time delay and the embedding dimension, but in fact, we're not going to use either of those. So we choose n equals 3 just for ease of visualization. We just want to view this thing. So if the blood pressure signal is x, then we define two new coordinates, y as t minus tau, and z as x of t minus 2 tau. Now we can plot a trajectory out in a three-dimensional phase space. And then it looks something like this. So here we've got 3 points, x is the first one, y at a fixed distance behind is the second one, and z at the same distance from y is the third one. As they chase each other through the signal, we can plot out in a phase space x against y against z, and we get this three-dimensional representation. So obviously if this signal is periodic, we go around the same loop every time in this phase space, but it's a true blood pressure signal, so it's not exactly periodic. We've got some variability, and you can see that variability in this attractor. if we take this 10 seconds of blood pressure data, then we get this attractor here in the phase space. So it's a bit messy. So what can we do about that? Well, there's a lot of baseline variation in the signal. So that's due to maybe the person or animal being active, resting, and so on. There's natural variation in this blood pressure. So we get a non-stationary signal, and so we want to try and remove the baseline variation. Now, the literature is full of complex algorithms for determining and removing this baseline variation, but we try to take a fairly simple approach. Suppose we just take our signal and we shift it vertically by a constant amount. X goes to x plus c. Then, of course, there's a similar shift in y and z. And so in our phase space, x, y, z, each variable gets c added to it. And so that's a shift along this diagonal direction, 1, 1, 1. So vertical movement in the signal results in a translation in the phase space in this direction, 1, 1, 1. So simply to eliminate baseline variation, we project our attractor onto a plane perpendicular to this 1, 1, 1 vector. And you do the algebra, you come up with 3 new variables, an orthogonal coordinate system, and v and w is the plane perpendicular to the vector 1, 1, 1. And so if we shift our signal by c, then that's picked up by the variable u, but v and w are unchanged. So we can now plot a 2-dimensional attractor in the VW plane. And it looks something like this. So now we've got our 3 points again, plot out the 3-dimensional attractor, but we're now viewing this down the direction of this 1, 1, 1 direction, and that corresponds to this. And so that line is the dot in the middle, and we're going to go from 3 dimensions down to 2 dimensions. Again, we can see the variability in the signal. But you might well say, well, baseline wonder isn't a simple vertical shift. What on earth are we doing this? This is too simplistic. Well, let's look at it another way. Let's take the Fourier transforms of our variables. So the Fourier transform of x gets multiplied by a frequency response function, and it gives the Fourier transform of u. Similarly for v and for w. So our frequency response functions are these. So fv is 0 or 0, and so the low frequencies are getting cancelled out, or at least damped down. And similarly, f of w, the low frequencies are being suppressed. But on the other hand, u has got all the low frequencies. It's keeping them. So fv and fw filtering out low frequencies in the signal. So maybe it's not such a daft thing to be doing after all. So if we look again at this signal, then the u variable is precisely picking up that baseline variation. It's picking up the low frequencies in the signal, but the v and w variables are very uniform and not affected by this baseline wander. So our plots in the phase space, there's a lot of movement in this diagonal direction. When we view it down this way, then we get this plot in the VW plane, and some of the variation has been removed. The final stage is to construct a density in the VW plane, because that's more useful than the blur of lines. And we've given that density a fancy name. We've called it a cardiomorph. We now have to choose the time delay. So there's lots of methods in the literature, but a popular method is the method of minimizing mutual information. But we're not going to use that. But the shape of our attractor does vary considerably as we vary the time delay. So what's the best one to choose? Well, we want to choose tour that makes the attractor as uniform as possible. Now, what do I mean by as uniform as possible? Well, if we take a periodic signal, then a closed orbit, then the trajectory in the phase space is a closed orbit. And that's both in three-dimensional XYZ space and on the VW plane. As a simple example, let's just take a sine wave where we've got period 1. So what we're going to do is plot out the trajectory associated with the sine wave for varying values of tau, the time delay. And what we get is this. So various changes occurring as tau varies. But you could argue that the orbit is quite uniform when tau is equal to a third, because that corresponds to a circle. And similarly, when tau is 2/3, that corresponds to a circle again. So that seems to be the most uniform cases for the circle, for the sine wave, which give a circle. Now, if we take any periodic signal, not a sine wave, with period t, and we take tau as the same values of t/3 or 2t/3, then we've got a result that says that the orbit generated in the VW plane is not circular, of course, in this case, but it's got Z3 symmetry generated by rotation of 2π/3 about the origin. And so for this periodic ECG signal, you can see this Z3 rotational symmetry in the plane. So this is giving this attractor a bit of structure to it. So, well, of course, no physiological data is periodic. So for approximately periodic data, we find the average cycle length, and we say the attractor will then be as uniform as possible if we choose tau to be 1/3 or 2/3 of the period. And so these are these two cases here. We can see the approximate symmetry in both cases. And now we fix that, then any changes in the attractor will not be due to a change in cycle length, but will reflect changes in the morphology of the signal. So we called this approach to generating an attractor the symmetric projection attractor reconstruction method. And it can be applied to any approximately periodic signal, whether from cardiovascular system or respiration or an engine or anything which is approximately periodic. And any changes in the morphology of the waveform are going to result in a change in the attractor. So we're capturing all the information about the waveform in this bounded attractor. So let's look at some machine learning then. So the question we're now going to ask is, can we distinguish between a wild-type mouse and a mutant mouse from their ECG signal? So this SCN5A plus-minus mutation is associated with sudden cardiac death. So if this was human ECGs, then we could possibly have a diagnostic tool just from someone's ECG that would say if they had this mutation. So what we've got here is two signals. The top is from a wild-type mouse, and the bottom one is from a mutant mouse. And the signals do look a bit different, but when we look at the attractors, then we can see they're very different. But of course, this is only an example of one wild-type and one mutant mouse. So the trick is to get a consistent classification for different animals. So our approach is to turn ECG signals into attractors. And we're going to use supervised machine learning to distinguish between them. And we're going to do two types of machine learning. We're going to manually extract features from the attractor, use machine learning on those, or alternatively, we give the images to a deep learning approach, deep neural network, to see how well that does. Our data consists of just 78 ECG signals. That's 42 wild type and 36 of the mutant. So the classes are approximately balanced. So in order to generate a bit more data, we took 130 seconds of data from each signal and divided it into 13 windows of 10 seconds each. An attractor was generated for each window. In this case, so we've got 13 images per animal, and so we now have 1,014 images. So 74 features were extracted from each attractor, and forward feature selection was used because we want to reduce the number of features, because if you use all of them, machine learning doesn't do so well. And we reduced the number of features up to a maximum of 20. So we used leave one out cross-validation, where all the records for one animal were removed, and that was for testing, and the rest was used for training. Obviously, we repeat that for each animal. For the machine learning, we used k nearest neighbors. We did also use SVM. We gave similar, not quite as good results. Now, obviously, we've got 13 records per animal, and so we're classifying each record individually. And to get a classification for the animal, we're going to use majority vote from those 13 records. As a comparison, we wanted to use standard ECG intervals and amplitudes. This is a standard analysis of ECG signals. They label various points on the signal P, Q, R, S, and T. And then intervals are found between these points, for example, PR, QT, and so on. And the amplitudes is the height, maybe of the R peak, height of the T wave, and so on. So 7 amplitudes and 6 amplitudes were derived from each signal as an alternative set of features. And machine learning was applied to these as well. Now the intervals and amplitudes, the accuracy by record was 83%, and when you use majority vote on the animal, it got 86% right. SPAR, on the other hand, got 86 and 87, so it wasn't much different. But when we combined them, then we got the best result of 91 and 96%. So if these features are looking at the signal in a different way, so when we combine them, we get the best result. We broke the data down by age and by sex and compared them. And again, you can see the results here. And again, they're doing much better for the combined features in all the groups. So there's one group does badly here, one group badly here, but consistently they're doing well in the combined group. We also looked at the distribution of votes for the majority vote, and red are the ones with less than 7 votes that are incorrectly classified, and the green are the ones that are correctly classified. This was intervals and amplitudes, SPAR, and when we combine them, then most get 13 out of 13 correct. A few get a smaller number correct, and a couple are stubbornly there at 0 votes correct out of 13. We tried a similar approach to see if we could classify sex as male or female from these signals in a similar way. And in this case, the accuracy by records of the intervals and amplitudes was 68%, by animal was 72%, and SPAR was quite a big improvement on that, with 77 and 83%. Interestingly, in this case, combining them didn't really give any significant improvement, and in fact, by animal was actually worse. So in this case, that was of no benefit. So that's machine learning with manual features. Now we tried deep learning that will automatically extract features from images. We've only got a small amount of data, nothing like enough to train a deep neural network. And so we used transfer learning with pre-trained networks. We used 3 networks, AlexNet, GoogleNet, and ResNet 18. And again, we had 13 images for every animal. In this case, we used cross-validation with 18 folds, but making sure, of course, that all 13 images were in the same fold. So we don't want some images for an animal in the training set and the test set. We used Bayesian optimization of the cross-validation error to find optimal values of 4 of the hyperparameters. And the results are going to be compared with those that we got obtained previously with the manual features. So these are the results previously. We obtained for genotype and sex. And the best results for the deep neural network were with GoogleNet. And these are roughly comparable, just slightly worse than with manual features, but broadly comparable. But the other two networks, Google AlexNet and ResNet-18, performed worse. So finally, the method can be generalized. We've talked to higher dimensional embeddings. We've talked about n equals 3 exclusively so far, but we can generalize it to n equals 4, and then we get 4-fold rotational symmetry, n equals 5, and a 5-fold rotational symmetry, and so on. And we can generate images for all these different n values of the embedding dimension, which give nice pretty pictures, at least. So, to conclude, symmetric projection attractor reconstruction provides a way of transforming an approximately periodic signal into an image which we can use with machine learning. And the whole morphology of the signal is encapsulated in the attractor, so any changes in the shape of the signal will result in changes in the attractor. So the images can be used directly for supervised machine learning using deep learning, or alternatively, we can extract features from the attractors and use it with machine learning. And I'll leave you with a few references. Thank you very much.